I, Dr. Jyoti Pillai, Billa Institute of Technology, will be discussing on the topic graph traversal. Graph is a data structure that consists of a set of nodes, vertices, points and a set of edges. A graph is defined as G equal to VE, where V is a set of non-empty set of vertices or nodes. E is a set of edges used to connect these vertices or nodes. The vertices could be internal graph elements or external elements represented by integer indices or references. The set of edges describes relationships among vertices or nodes. There are some terminologies which will be used in the graph traversal. First one, adjacency. Adjacent or neighbor nodes are connected to each other through an edge. Both vertices or nodes are endpoints of same edge. For example, in graph G1, vertex V1 has two adjacent vertices V2 and V3. Adjacent edges, two distinct edges that share an end vertex. In graph G1, edges E1 and E2 share same end vertex V1. Cycle is a path from a vertex to itself. A graph is called cyclic if it contains a cycle, otherwise it is called cyclic. In a graph terminologies, we will be seeing an example of cycle. In this particular graph, there forms a cycle between the nodes 1, 2 and 4 and another cycle from 4 and 5. A graph G equal to VE is called a non-directed graph if all edges present between any two nodes are non-directed. In non-directed graph, undirected edge has no orientation, that is no arrowhead. There is a difficulty to identify starting and ending nodes of the edge in the case of non-directed graph. For example, in the graph there are 4 vertices A, B, C, D and 4 edges between the vertices which are not directed. Edge between the vertices A and B does not have any direction. So, cannot be determined whether edge starts from A or it starts from B. We cannot determine the ending vertex of an edge between A and B. A graph G which has every edge mapping onto some ordered pair of vertices V1, V2 or Vi, Vj is called a directed graph or digraph. All edges of a digraph are directed. In directed graph, it is easy to determine from which node it is starting and which node it will be ending. Directed edge has an orientation, that is, has an arrowhead in the case of directed graph. For example, in the graph, there is an edge E1 from V1 to V2. E2 edge starts from V2 and ends at V3. The starting node of E4 edge is V2 and ending node is V4. An adjacency list represents a graph as an array of linked lists. The index of the array represents a vertex and each element in its linked list represents the other vertices that form an edge with the vertex. For example, in the graph there are 4 vertices 0, 1, 2, 3 and the adjacency list of the vertex 0 are 1, 2 and 3, where 1, 2 and 3 are adjacent nodes of 0. In the adjacency list of 1, the nodes are 0 and 2. Adjacency list of 2 will have the nodes 0 and 1 and adjacency list of 3 will be having 0 as its adjacent node. Graph traversal is a technique which is used for searching a vertex in a graph. Graph traversal means visiting all the nodes of the graph at least once. Graph traversal is used to decide the order of the vertices visited in the search process. It helps to find edges to be used in the search process without creating loops or cycles. There are 2 types of graph traversals, depth first search and breadth first search. Both breadth first search algorithm and BFS algorithm works on directed or undirected graphs. Many advanced graph algorithms are based on the ideas of BFS or DFS. Each of these algorithms traverses edges in the graph, discovering new vertices as it proceeds. Today we will be discussing on breadth first search algorithm. BFS is a graph traversal algorithm that begins searching from a particular node as starting node or root node. BFS explores all vertices of a graph at a given depth level before moving on to next depth level. Starting from a given source vertex, BFS explores all its adjacent vertices, then adjacent vertices of these vertices and so on until all vertices reachable from the source vertex are visited. When exploring a particular level, BFS selects nearest unexplored node from current node to explore next node. BFS uses a queue data structure to keep track of the vertices that need to be explored next. A queue is an abstract data structure that follows the first in, first out, that is FIFO methodology. That is, one end of the queue is used to insert the data and the other end is used to delete the data. That is, whichever data element comes first will be served first. BFS is useful in finding shortest path between two vertices in an unweighted graph and can also be used to detect cycles in a graph. BFS is the most popular traversal approach. This recursive algorithm is used to search all vertices in a tree or graph data structure. There are some essential features which makes the BFS algorithm necessary to be used. BFS algorithm has a simple and reliable architecture. BFS helps evaluate nodes in a graph and determines the shortest path to traverse nodes. BFS algorithm can traverse a graph in the fewest number of iterations possible, reducing the total time duration. The iterations in BFS algorithm are smooth and there is no way for it to get stuck in the infinite loop. In comparison to other algorithms, BFS algorithm results has the highest level of accuracy. In BFS, traversing the graph is done breadth-wise as it follows. First, move horizontally and visit all the nodes of the current layer, then move on to the next layer. A standard BFS implementation puts each vertex of the graph into one of the two categories: visited, second not visited. The purpose of the algorithm is to mark each vertex as visited while avoiding cycles. BFS algorithm rules, that is, there are some BFS algorithms rules to be implemented. That is, first is queue. Use a queue data structure to keep track of visited nodes. Visited marking, that is, maintain a visited array or a set to keep track of the vertices that have been visited during the traversal. Enqueue and mark. Enqueue the starting vertex into the queue and mark it as visited. Dequeue and visit neighbors. While queue is not empty, dequeue a vertex, visit it and enqueue it into the unvisited neighboring vertices. Order of visit. Visit vertices in the order they were enqueued, ensuring a breadth first exploration. Avoid revisiting. That is, check if a node has been visited before enqueuing it to avoid revisiting vertices. Termination. Terminate the BFS algorithm when the queue becomes empty, indicating that all reachable vertices have been visited. Shortest path. If finding the shortest path using BFS algorithm, track the parent of each vertex to reconstruct the path once the destination is reached. The BFS algorithm works as follows. Step 1. Start by putting graphs any one of the vertices at back of the queue. Step 2. Take the front item of the queue and add it to the visited list. Step 3. Create a list of that vertex adjacent nodes. Step 4. Add those which aren't in the visited list to the back of the queue. Step 5, repeat 3 and 4 until queue is empty. Let us consider an elaborated steps of BFS algorithm. Step 1, begin by choosing a graph to navigate. That is, first of all, consider that graph which has to be traversed, all the nodes of that graph has to be traversed, find it out. Step 2, select the starting vertex to traverse the graph. Step 3, choose 2 data structures to use for traversing the graph. 1, a visited array of size equal to number of vertices in the graph. 2, a queue data structure. Step 4, start with chosen vertex and add it to the visited array. Enqueue all adjacent vertices of the starting vertex into the queue. Step 5, remove first vertex from the queue using first in first out approach, add it to the visited array and enqueue all of its unvisited adjacent vertices into the queue. Step 6, repeat step 5 until queue is empty or there are no unvisited vertices left. Let us consider an undirected graph with 5 vertices for implementing BFS. In this undirected graph, there are 5 vertices 0, 1, 2, 3 and 4. We will consider 2 arrays, one visited list, second a queue data structure. Starting from the vertex 0, any arbitrary vertex can be chosen. So, we are choosing the vertex 0. BFS algorithm starts by putting it in the visited list. So, visited list will be containing the item 0 or the node 0. Then put all its adjacent vertices in the queue. Adjacent vertices of 0 are 1, 2 and 3. So, queue will be consisting of 1, 2 and 3 with 1 at the front side. Next, visit the element at the front of the queue, that is 1, and then go to its adjacent nodes. Since 0 has already been visited, visit 2. 1 is put in the visited list and now front is pointing to the node 2 in the queue. Vertex 2 has an unvisited adjacent vertex, that is 4. So, add it to the back of the queue. Visited list consists of elements 0, 1 and 2. Queue consists of elements 3 and 4 with front pointing to 3. So, now visit 3 which is at the front of the queue. Only 4 remains in the queue since the only adjacent node of 3, that is 0, is already been visited. Hence, visit 4. Now, the visited list will be consisting of 0, 1, 2 and 3 and queue will be consisting of only single element, that is node, that is 4, and front is pointing to 4. Now, 4 is put in the visited list, making the queue empty. And now, since the queue is empty with no elements present in the queue, the breadth first traversal of the graph is completed. Let us consider another example. In this graph, there are 6 nodes 0, 1, 2, 3, 4 and 5, starting with 0 again as the root node. In the first iteration, enqueue 0, that is add 0 into the queue. So, queue after iteration 1 will have 1 node 0. Iteration 2, dequeue 0, that is remove 0 and put it in the visited list and add adjacent nodes of 0, 1, 3 and 4 into the queue, that is enqueue 1, enqueue 3, enqueue 4 into the queue. Queue after iteration 2 will be having 3 nodes 1, 3 and 4. Iteration 3, now dequeue 1, removing 1 from the front end of the queue. Enqueue 2, Q after iteration 3 will be having 3 nodes, 3, 4 and 2. Iteration 4, DQ 3, NQ 5, 5 is the adjacent node of 3. So, Q after iteration 4 will be having nodes 4, 2 and 5. Iteration 5, DQ4, Q after iteration 5 will have 2 nodes 2 and 5. In the next iteration 6, DQ2, Q after iteration 6 will have a single node 5. Iteration 7, DQ5, so Q after iteration 7 will be empty and all the nodes in between 0 and 5 or all the nodes of the graph have been traversed, and then if the queue is empty, stop the BFS process. Now, we will consider the steps involved in BFS algorithm to explore a directed graph. Step 1, set status is equal to 1, that is ready state for each node in the graph G. Step 2, NQ the starting node A and set it to status 2, that is the waiting state. Step 3, repeat steps 4 and 5 until Q is empty. Step 4, DQ a node N, process it and set its status equal to 3, that is processed state. Step 5, NQ all neighbors of N that are in ready state, that is status is equal to 1, and set them as status equal to 2, that is waiting state. Here the loop ends. Step 6, exit. Let us consider an example of BFS algorithm on a directed graph. This directed graph has got 7 vertices A, B, C, D, E, F and G. First of all, create adjacency list for each of the vertices. Adjacency list will be consisting of adjacent nodes of each of the nodes. So, A, B, C, D, E, F and G will be having its own adjacent nodes, that is those nodes which are adjacent to each of them. Minimum path can be found by using BFS, and that will start from node A and end at node E. Two queues Q1 and Q2 are used. Q1 holds all the nodes that are to be processed. Q2 holds all the nodes that are processed and deleted from Q1. Start examining the graph starting from node A. Step 1, first add A to Q1 and null to Q2. That is, Q1 will be equal to A and Q2 will be equal to null. Step 2, delete node A from Q1, that is DQ Q1, and add it to Q2. Insert all neighbors of node A to Q1. Adjacent nodes or neighbors of node A are B and D. So, they are put in Q1. So, Q1 will be equal to B and D and Q2 equal to A. Q2 is the list of visited nodes. Step 3. Now, delete node B from Q1 and add it to Q2. Q2 is the list of visited nodes. So, Q2 will be now consisting of A and B. Insert all the neighbors of node B to Q1. Q1 will be having elements D, C and F now. Step 4. Now delete node D which is at the front of the queue from Q1 and add it to Q2. Insert all neighbors of node D to Q1. The only neighbor of node D is F, since it is already inserted. So, it will not be inserted again. So, now Q1 will be having C and F, Q2 equal to A, B, D. Step 5. Delete node C from Q1 and add it to Q2. Insert all neighbors of node C to Q1. So, Q1 will be equal to F, E, G. Q2 will be equal to A, B, D and C. Step 6. Delete node F from Q1 and add it to Q2. Insert all neighbors of node F to Q1. All neighbors of node F are already present. Do not insert them again into Q1. So, Q1 will be equal to E, G, Q2 will be equal to A, B, D, C, F. Step 7. Delete node E from Q1. Since all of its neighbors have already been added, will not be inserted again. Now, all the nodes are visited and the target node E has been encountered into the Q2. Complexity of BFS. Time complexity. The time complexity of BFS is OV plus E, where V is number of nodes in the graph and E is number of edges in the graph. When dequeuing from its queue or exploring its adjacent vertices, BFS attempts to visit all nodes and edges at least once. Thus, its time complexity increases linearly as more nodes and edges enter or exit it. The space complexity of the breadth first search algorithm is OV, which grows linearly with number of vertices in the graph G. V is represented as an integer value because even under extreme conditions, BFS Q can simultaneously contain all vertices in its maximum level traversal. Let us see advantages of BFS. BFS is guaranteed to find the shortest path between the source and any other vertex in an unweighted graph, which makes it a useful algorithm in finding the shortest distance between 2 points, such as in navigation or routing problems. BFS is a complete algorithm, which means it will always find a solution if one exists. BFS is used in various applications such as social network analysis, web crawling and image processing. BFS can handle disconnected graphs by exploring each connected component one by one. BFS can be easily parallelized, which means that it can take advantage of multiple processors to speed up the search. Disadvantages of BFS. BFS requires more memory than DFS as it needs to store all the nodes at each level. BFS can be slower than DFS, especially when the graph is dense. BFS may not be suitable for large graphs as it can become slow and memory intensive. BFS may not be the best algorithm for pathfinding in weighted graphs as it may not always find the shortest path. There are various applications of BFS. First application, shortest path and minimum spanning tree for unweighted graph. In an unweighted graph, the shortest path is the path with the least number of edges. With BFS, we always reach a vertex from a given source using minimum number of edges. Also, in case of unweighted graph, any spanning tree is minimum spanning tree and we can use either DFS or BFS to find a spanning tree. Second application, to find minimum spanning tree for weighted graphs. We can also find minimum spanning tree for weighted graphs using BFT, but the condition is that weight should be non-negative and same for each pair of vertices. In peer-to-peer networks also, like BitTorrent, BFS is used to find all neighboring nodes. BFS can be used for finding crawlers in search engines. Crawlers build an index using BFS. The idea is to start from source page and follow all links from the source and keep doing the same. DFT can also be used for crawlers, but the advantage of BFT is the depth or levels of the built tree can be limited. In social networks also, we can find people within a given distance k from a person using BFS till k levels. BFS is used to find all neighboring locations, that is, BFS can be used in GPS navigation systems. In networks, a broadcasted packet follows BFS to reach all the nodes. Hence, BFS can be used for broadcasting in the network. BFS can be used in garbage collection process also. BFS is used in copying garbage collection using Cheney's algorithm. BFS is preferred over DFS because of a better locality of reference. BFS can be used for cycle detection in undirected graph. In undirected graph, either BFS or DFS can be used to detect a cycle. BFS can also be used to detect cycle in a directed graph. Ford-Fulkerson algorithm. In Ford-Fulkerson algorithm also, we can either use BFT or DFT to find the maximum flow. BFT is preferred as it reduces the worst case time complexity to OVE raised to 2. BFS can be used to test if a graph is bipartite. We can either use BFS or DFS algorithm to check whether the graph is bipartite or not. BFS can be used in pathfinding. We can either use BFT or DFT to find if there is a path between two vertices. BFS is used in finding all nodes within one connected component. We can either use BFT or DFT to find all nodes reachable from a given node. In AI, that is artificial intelligence, BFS is used in traversing a game tree to find the best move. In the field of network security, BFS is used in traversing a network to find all the nodes, all the devices connected to it. We can find all the connected components in an undirected graph using BFS. BFS can be used for topological sorting also. That is, BFS can be used to find a topological ordering of the nodes in a directed cyclic graph, that is DAG. BFS can be used in image processing. BFS can be used to flood fill an image with a particular color or to find connected components of pixels. BFS can be used in recommended systems also. BFS can be used to find similar items in large data set by traversing items connections in a similarity graph. There are various other usages of BFS algorithm. Many algorithms like Prim's minimum spanning tree and Dijkstra's single source shortest path use structures similar to breadth first search. So, we have seen that there are various applications of BFS. Breadth first search algorithm can also be used for disconnected graph. BFS is a graph traversal algorithm that visits all the vertices of the graph in a breadth first order. That is, it visits all the vertices at the same level before moving to the next level. For a disconnected graph, there may be multiple connected components, that is subgraphs that are not connected to each other. To perform BFS on a disconnected graph, we need to apply BFS on each connected components separately. BFS on a disconnected graph follows the following steps. Step 1, initialize all vertices as not visited. Then step 2, for each vertex that is not visited, apply BFS starting from it and mark all the visited vertices. Step 3, repeat step 2 until all the vertices are visited. Now, let us consider the difference between BFS and DFS by considering various parameters. The first parameter is traversal. BFS traverses a graph level wise, whereas DFS traverses a graph depth wise. Second parameter, search order. BFS visits nodes in order of distance from the source node. DFS visits nodes in order of their depth from source vertex. BFS visits all nodes at a given level before moving on to next level. DFS visits all nodes along a path starting from the node or as far as possible before backtracking. Usage or database. BFS uses a queue to store the vertices to be visited and hence requires more memory than DFS, whereas DFS uses a stack to store the vertices to be visited and hence uses less memory than BFS. Completeness. BFS is guaranteed to find shortest path between source and any other vertex in an unweighted graph. DFS may not find the shortest path and may get stuck in an infinite loop. Suitability. More suitable when target node is closer to source node, more suitable when target node is away from source node. BFS is used to find shortest path, DFS is used when memory usage is a concern. Thank you.